I'd like to start by thanking the organizers for giving me the opportunity to speak at what's already been a terrific conference. They charged me with a difficult task, which is to review all of string cosmology in 1 hour. And this is a complicated subject with a rich landscape of topics, some of which we've already heard about, and some of which we'll be hearing about later today. My focus is going to be particularly about inflation in string theory, and to some extent also, later in the talk, on cosmological singularities and on ideas for avoiding those singularities. This list here that I've presented is not even itself complete. So I want to stress that what I'm really giving is a picture of some of the things that have been happening in string cosmology and not the entire story. So the plan for the talk is to start with a brief review of why cosmology is interesting now, why this is an interesting time observationally and as a theorist. I'll then explain why it's interesting specifically to be a string theorist working on cosmology. What does string theory have to say, and how can it interact with the coming generation of observations? The main topic will be inflation in string theory. Now, although this is the home of Linnaeus, I'm not going to take a botanical approach. I will not attempt to describe the range of models of inflation in string theory with their various achievements and challenges. What I'm going to do is talk about the main problems. What are the tasks? What do you need to do to build a model of inflation in string theory? And that will equip you to draw your own conclusions about the models in the literature. So I'm going to illustrate these problems and the achievements in two classes of models of inflation involving D-branes, D3 branes particularly, and then models of Axion inflation. After talking about inflation in string theory, I'll move on to discussing the initial singularity and alternative cosmologies. So we are really living in a golden age of cosmology. We're fortunate to have a wide range of impressive experiments ranging from surveys of large-scale structure to the famous WMAP pictures of the temperature anisotropies in the cosmic microwave background, the polarization of the cosmic microwave background, and then Planck, which should be giving us fairly soon a vastly improved picture of the CMB. So far, they've only given us a picture of the foregrounds. Now, one can get the impression that this is all about WMAP and Planck, and that's far from the case. In fact, many of the early achievements earlier in this decade and at the end of the last were by suborbital experiments, and there are many of those now that hold the promise of doing much better than Planck on certain kinds of things. So overall, this is a robust experimental field. And in fact, if you don't believe me that it's a golden age of cosmology, you can see this one-line Wikipedia entry, which tells us that the golden age started in 1992. And 1992 is when COBE detected the cosmic microwave background anisotropies. So we talked just now about the experimental situation. What's the theoretical status? Well, as we all know, the late universe, the acceleration of the late universe, presents a tremendous challenge for our ideas about naturalness. And I'll say nothing more about this today. The early universe, well, here we have an extremely successful paradigm, inflation, which made a number of predictions that have been borne out in experiments. But inflation is sensitive to Planck scale physics, and it's therefore best described in a theory of quantum gravity. This will be one of the main points of the talk. I'll try to explain what this point means and how we go about describing it in string theory. And at this point, we have an embarrassment of riches. We have a huge array of inflationary models with different properties, some of which I will talk about. And what we would like is some way to impose some sort of structure on that, to understand which ones are reasonable ones, which ones are well-motivated. And finally, alternatives to inflation, to the extent that these have been constructed, are overshadowed by microphysical questions. These are questions that we could try to address in string theory. For example, the questions of singular bounces. So I'm going to emphasize these 2 points. Let's review inflation briefly. I'm going to talk only about the simplest case in this review at the start of the talk, and then I'll talk about more complicated models soon. So the model that's easiest to describe is a model in which there's a single scalar field that's canonically normalized and has some potential. And as you've doubtless heard, if the potential obeys appropriate flatness conditions, so if its curvature and slope are suitably small in Planck mass units, then the potential can drive a phase of accelerated expansion, a quasi-exponential phase, a quasi-de Sitter, with exponential expansion governed by a constant h, h, the Hubble parameter, I'll be referring to throughout as Hubble or h. This is the most important scale in this discussion, so everything is going to be related to h. And in particular, this slow roll condition, that the curvature should be small, really means that the inflaton mass term should be small compared to h squared. That's a comparison to bear in mind for the rest. So we're not really that excited about the background story in inflation, although that was certainly part of, that was essentially all of the original motivation. The exciting thing at present is the fact that inflation predicts a spectrum of scalar perturbations and tensor perturbations. So if we take the spatial part of the Friedmann-Robertson-Walker metric and write it like this, so zeta is a curvature perturbation, then we can compute the two-point function of the curvature perturbations. And in Fourier space, it can be represented in terms of a power spectrum. This power spectrum you can conveniently write in terms of an amplitude, AS, it's some reference wave number, times a power law dependence. This is called the tilt. Now, these primordial anisotropies that inflation produces undergo acoustic oscillations in the first 380,000 years. And at the end of that period, the universe is cooled sufficiently so that electrons and protons recombine, or rather combine for the first time, although it's called recombination. This period of decoupling is when the CMB is released to us. The universe becomes transparent. So we now have incontrovertible evidence for those acoustic peaks. And the evidence is increasing right now. So in detail, these predictions, this is actually going to be important for us to examine this briefly, because we'd like to understand how can this structure here tell us about something more than plasma physics. I mean, the acoustic oscillations are very nice, but they really have to do with electrons, photons, baryons, and dark matter. What do they have to do with ultra-high scale physics? In dynamics, not much, but by looking in detail at the structure of these acoustic oscillations, we can probe the detailed structure of the primordial anisotropies. So the predictions of inflation are that the universe on large scales should be homogeneous, isotropic, and flat. And indeed, it is homogeneous and isotropic. For example, note that the anisotropies here are measured in microkelvin compared to the 2.7 Kelvin background. So it's rather homogeneous. It's also flat. If you look at this peak, this first peak represents the size of the horizon at the time of decoupling. So we can compute how large that is, we can compute how far that is, and by comparing those two things to the observed angular size, represented here in terms of multipole expansion, L, we can deduce the curvature of the universe that intervenes. And so we can deduce that the universe is very close to flat. So this is very nice. So much for the background. Now, about the perturbations. So the perturbations are Gaussian. We haven't yet seen any evidence for a three-point function. We just have upper bounds. The perturbations are adiabatic. You heard about this in the talk by Wilczek. That means that there are no isocurvature perturbations to the level measured so far. And isocurvature perturbations are perturbations in which, for example, the density of dark matter increases and density of photons decreases, keeping the total density fixed. Instead, we just see overall curvature perturbations. The perturbations are nearly scale invariant. We have rather strong constraints now on the deviations from scale invariance. And it looks like in the near future we should get firm evidence that the universe, well, that the primordial perturbations are just slightly deviating from scale invariance, which is totally consistent with the predictions of inflation. And finally, and this is most exciting really, the perturbations are correlated on superhorizon scales. So to understand this, we need to look at the polarization of the CMB, depicted here. And rather than writing the power spectrum of the polarization itself, I'm going to write the correlation function of the temperature anisotropies and one component, the E-mode component of the polarization. What inflation predicts is that these two components should be anti-correlated on large scales. So going back, remember that this size here, right here, this angular size, is the horizon size. Anything to the left here is superhorizon scales. It was outside the horizon at the time of decoupling. And what we see here is that the prediction is perfectly borne out. These two things are, the temperature and polarization anisotropies are anti-correlated on superhorizon scales. So this is really compelling evidence for some sort of mechanism, of which inflation is by far the most exciting, for generating superhorizon correlations. So the primordial perturbations are also well tested as the seeds for large-scale structure. And we can use these observations as windows on the physics of inflation. Going beyond the simplest kind of model, we can ask, what if we do see deviations from the simplest picture, from Gaussian adiabatic perturbations with vanishing primordial gravitational wave perturbations? This is really where the fun starts, because if the perturbations are Gaussian, we're really just probing free field behavior. It's the non-Gaussianity that probes the interactions. If we see deviations from adiabaticity, that would show us that there were multiple fields that are light during inflation. When you have only one field that's light, you have one clock, and the only thing that you can create is a curvature perturbation. And this one is the most interesting for string theory, although I should stress that Gaussianity and non-Gaussianity are also very important. In my mind, this is particularly interesting. R here is the tensor to scalar ratio. That's the ratio of the power in tensor perturbations, primordial gravitational waves, to the power in scalar perturbations. The amplitude, R here, directly reveals the energy scale of inflation. And if you check, you find that we would be able to detect primordial gravitational waves only if inflation occurred at the gut scale, and also, and this is even better, only if the inflaton traversed a super Planckian distance in the last 60 e-folds of inflation. So we'll come back to that, and we'll say much more about that. So what Leith pointed out in '96 is that the tensor to scalar ratio can be written as bounded above by 10 to the minus 2 times the inflaton distance traveled during the last 60 e-folds in Planck mass units squared. So this 10 to the minus 2 is about the best we can expect from even a relatively futuristic experiment measuring the tensor modes. So what this is telling you is that if we ever see tensor modes, we know the inflaton has moved over a super Planckian distance. And that's exciting for Planck scale physics. So I hope I've convinced you so far that all of this is very exciting in terms of cosmology. This is an interesting time to be studying the early universe. But what does all of this have to do with string theory? Why should we be using string theory in cosmology? This is, of course, one of the main points of the talk, to try and explain to you why we would be doing this. The key point is that inflation is sensitive to Planck scale physics. What I mean by this is that the dynamics is controlled, generically, by non-renormalizable contributions to the effective Lagrangian. Why are there non-renormalizable contributions? Well, we expect that on very general grounds from integrating out some massive species to which the inflaton couples. Why are there massive species? Well, the ultraviolet completion of gravity should really furnish us with some new degrees of freedom with a cutoff scale at or below the Planck scale. So in string theory, we certainly have this. We have string modes, we have Kaluza-Klein modes that are well below the string scale. And so in string theory, the mass that's relevant here, lambda, is going to be below the Planck scale. But let's just be conservative. Let's push this cutoff all the way up to the Planck scale. Then if we take order unity couplings, then one finds, as I'll show on the next slide, that there's a class of operators with dimension 6 or smaller that make really critical corrections to the dynamics. Incorporating these operators can totally change whether inflation even occurs. So it's in this sense that inflation is sensitive to the UV completion of gravity, and this is our opportunity. So this is worth some explanation. Let's consider a simple model. This is not the only place where we can, this simple model is not in itself the complete story, but it gives us a good sense of exactly what kind of thing can happen. It gives a more concrete picture to the words that I presented on the last slide. So consider a Lagrangian of this form. Again, a single scalar field with canonical kinetic term and some potential. And let's imagine that that potential is the renormalizable part of the potential, V0. Now let's consider the contribution of a non-renormalizable term with dimension delta that happens. And this is the point where we're referring to a class of operators rather than all possible operators. This is an operator that happens to be proportional to V0 times the power of phi over the cutoff. Why are there operators like that? Well, it's hard to forbid them. V0 was already allowed. It's hard to also forbid phi to some even power, certainly. And so operators like V0 phi squared over m Planck squared are hard to argue away. If you include an operator like this, the correction to the inflationary eta parameter, which remember is the inflaton mass in units of the Hubble scale, looks like this. And for an operator of dimension 6, what we find is that this contribution is at least unity for order 1 couplings. So this is a serious issue. This says that if the inflaton moves over a small distance, if phi is small compared to m Planck, then at the very least we need to understand contributions to the effective Lagrangian that are of dimension 6 and smaller. In fact, 6 is not enough, right? If we understood dimension 6 operators, we would understand corrections to eta of order unity. In fact, we need eta of order 10 to the minus 2. So we better push it maybe to dimension 7 or 8, depending on how large phi over the cutoff is. But you'll easily see that if I take a model in which the inflaton moves over a super Planckian distance, then this description in terms of an expansion in powers of phi over m Planck breaks down terribly. This is not a useful description at that point. We would have to control an infinite series of corrections with arbitrarily large dimension. And the larger the dimension, the more important the contribution. So this is a heightened opportunity for sensitivity to Planck scale physics. And I think we'll hear much more about chaotic inflation models of this sort in the next talk. So it bears repeating, this is really a consequence of naturalness. This is not something very special or pathological about inflation. We should have expected it. The point is just that the inflaton mass, in the absence of a symmetry, will run up to the cutoff, and the cutoff is above the Hubble scale. So the inflaton mass will run up to at least the Hubble scale. That's the heart of the problem. This happens even in low-scale models with small inflaton displacements. It has nothing to do with the inflation or energies being high. It only has to do with the fact that inflation involves gravity. So what we need to understand is how can we get control of the inflaton action, including the effects of integrating out massive fields that are part of the UV completion of gravity. In string theory, what we need to do is work out what those massive fields are, take into account their effects, and the significant contributions in string theory notably include stabilized compactification moduli. These are the massive species that we need to integrate out. So that's a clear task. We need to understand moduli stabilization in detail. So now we come to inflation in string theory. The first thing we're faced with is the moduli problem. So in the simplest compactifications, we have a fatal instability in general. You've undoubtedly heard about the moduli problems in cosmology generally. If the moduli decay during Big Bang nucleosynthesis, they can destroy the light element production, they can overclose the universe if they linger too long after, et cetera. There's an additional problem in string theory, which is somewhat more severe. String theory also enjoys these problems, but in string theory, we also have an overall volume of a compactification. And that can undergo a decompactification instability in the presence of positive energy. So this is generally fatal, and this is what kills an awful lot of models, or would-be models of inflation in string theory. So the key development of the past decade in terms of building models of inflation in string theory is the growing understanding of methods for stabilizing the moduli. I want to stress that we don't just need to stabilize the moduli and find a vacuum. We need to then understand the effective theory of the stabilized compactification. So how do we go about doing that? We're going to start with discussing the stabilization itself, and here you actually heard a lot about this in the talks by Grania and Xu yesterday. So the approach that's been most fruitful so far, and this was started by KKLT, is to begin with a stabilized ADS4 vacuum, which may or may not be supersymmetric. In the KKLT model, it's supersymmetric. And then uplift, meaning incorporate an additional effect that breaks supersymmetry. So there are two steps here. We need two ingredients. We need something that stabilizes the moduli in anti-de Sitter space, and we need something that breaks supersymmetry. The challenge is the mechanism that produces controllably small supersymmetry breaking. After all, we have lots of SUSY breaking objects, but you can't just add an anti-brane that's not in a warp region. You'll break supersymmetry at the string scale, and this would ruin all kinds of control in the effective theory. So we need a mechanism producing a controllably small breaking, and this breaking had better not be just in global supersymmetry. That's because once we couple a global supersymmetry model for SUSY breaking to supergravity, the control parameters get promoted to dynamical fields, and those in general will experience some sort of instabilities of their own, which have to be controlled. So I'm not going to review this first point of stabilizing the moduli. What I hope you've gathered from yesterday is that it's challenging, and progress has been slow. And the other thing is that, so Grania told us we could draw our own conclusions about her results, and I think it's fair to say that comparing the difficulties found in the talk by Xu in type 2a and the apparently metastable, albeit infrared singular solution described by Grania, it seems like the best available tools at present for producing anti-de Sitter vacua, rather for uplifting anti-de Sitter vacua to de Sitter space, are anti-D3-branes in a warped region. So that's what I'll be focusing on later on. So realistically, what do we need to achieve? Realistically, we need to construct a compactification with stabilized moduli and derive the effective action and see that inflation occurs. One often hopes for more, but I'm not going to demand more. I'll just occasionally look for more. You might hope for distinctive signatures, for some natural mechanism, et cetera. And the important point to recognize here, and this is really the primary reason why progress in this field has been very gradual, is that compact models with no supersymmetry and stabilized moduli are very messy systems, and most of our usual tools fail. One also has to use a large number of approximations. So of course we use the long wavelength recoupling approximations. As you heard yesterday, you have to use a probe approximation, sometimes a smeared approximation, local approximations, et cetera, et cetera. And often in one model, one has to use many of these approximations at one time and try and show that they're compatible. And this is much of the challenge. So a common approach is to construct a naturally flat inflaton potential. I put that in quotes because if you construct an inflaton potential in a model with unstabilized moduli and just hope for the best, you don't know that it's naturally flat. You know that it's naturally flat except for some corrections that haven't been computed. And so although this approach is sincere, it's misdirected, and it's not clear what we're going to learn from it. So here's a very restricted list of some of the attempts to build a model of inflation in string theory. Based on the comments I made before about de Sitter space, you will understand that the presently best developed models are going to be set in type 2b string theory. After all, if we can't find a model of de Sitter space in type 2a just yet, how are we going to build a model of inflation, which is a little bit more tricky? Of course, we would all love to get beyond this and to study more general models. And that's, I think, a challenge for you in the audience to improve the status, the understanding of moduli stabilization and de Sitter space, both in type 2b string theory, but most particularly in other string theories, so that we can actually start to explore the possibilities for realistic cosmology in those other theories. So there are two basic approaches. One thing we could try and do is enumerate all the significant contributions in some computable example. The other thing we could try and do is identify a robust symmetry in a UV completion that protects the inflaton, so a real symmetry argument. And here too, there's a sort of a partial approach which one could take, and one often sees, which is you could enumerate some of the contributions, but not all of them. Or you could identify a symmetry that's broken by the UV completion, which, if it hadn't been broken, would have protected the inflaton. And these approaches, although they look good at first, are not going to be very good in the long run. So let's start with the first example. This is the lamppost example. The idea is to simplify our task by studying the effective theory of a local region of a stabilized compactification and use 10D locality to control the calculation. The key technical simplification I'll be making use of here is that in type 2b string theory, the best understood methods of moduli stabilization, which are the ones I just described, yield 10D solutions that can be formulated in a systematic expansion around conformally Calabi-Yau compactifications. So what are those? A conformally Calabi-Yau background is one in which we have a warped product of space-time. In fact, this should be Minkowski space here, and a Calabi-Yau space, so GMN is a Calabi-Yau metric. And we can find solutions in this class if the imaginary anti-self-dual part of the flux vanishes, if a particular scalar combination of the warp factor and the four-form potential vanishes, and if the dilaton gradients vanish. You should think of these solutions as solutions that either preserve the supersymmetry of D3-branes or almost preserve the supersymmetry of D3-branes. They're so-called pseudo-BPS. Now, these spaces provide some of the best studied examples of moduli stabilization, or the context for some of the best understood examples. What they really provide is a no-scale model in which the complex structure moduli and the dilaton are stabilized, but at leading order, the Kähler moduli are massless. There are then physical effects that can lift the flat directions in the Kähler moduli space. These are perturbative and non-perturbative effects. And the whole challenge in moduli stabilization is to gain adequate control of these perturbative and non-perturbative effects so that one can argue for a vacuum in a controllable regime. So that's a story that's been told many times, and I'm not going to say more about it. Now, these effects are typically treated in 4 dimensions, but they can be described in 10 dimensions. As for this, I'll refer you to my talk at Strings 2010. This was first proposed by Kerber and Martucci in 2007. And there have been some understanding since then of how we can use this to try and understand the effective action. So why do I mention this point that we can describe it in 10D? Well, once you can describe moduli stabilization in 10 dimensions, you can try and use 10-dimensional locality. And that's a powerful tool. So here's the trick. The moduli potential is small in string units, right? You knew that had to be the case because we had an effective theory description, a low-energy effective description. So we can use the smallness of the moduli potential as our expansion parameter. We're going to start with a conformally Calabi-Yau background and expand order by order, and systematically incorporate the effects of moduli stabilization. So the expansion parameter is this smallness. And we find something very interesting, which is if you expand to any order n, the full equations of motion for general conformally Calabi-Yau background, the equations of motion simplify dramatically. They're triangular. Okay. So what I mean by that, I'm going to illustrate it in a toy model. If you want to see the whole equations, you can just look in our paper. Let's consider a system of linear ordinary differential equations describing some number of fields phi a, which are functions of a single variable r. The superscripts denote the order in perturbation theory around some background phi 0 of r. So on very general grounds, what can the derivative of the nth order field phi a n depend on? Well, it can involve some matrix, which is 0th order, acting on the other nth order fields. And it can involve a source term, which is an nth order combination of fields that are lower order than n, for example, n over 2 and n over 2. Right, so that's quite general. Now, if this were a matrix of constants, this would be child's play. In general, it's not a matrix of constants. NAB depends on the 0th order background, which is a function of the independent variable. So you can't just make a change of variables to get rid of NAB and decouple all these equations. What can happen is you can be lucky. It can happen that in some systems, in some bases, which are hard to find in general, you can only find these nice bases by solving a system of differential equations of equal difficulty. In some systems, in some bases, things can be nice. For example, NAB can be diagonal or it can be triangular. And that's what we find. We find that the type 2b equations of motion expanded to any order around a conformally Calabi-Yau background are triangular. What that's good for is, once this thing is triangular, one of the fields is sourced by no other nth order fields. Let's call that the first field. The second field is sourced only by the first field and by fields lower order in perturbation theory. The third field is sourced by the second nth order field, the first nth order field, and all fields at lower order in perturbation theory, et cetera, et cetera. And so whenever you can solve the individual uncoupled equations, you can solve the coupled system. And we can do this at any order. In fact, this was the structure that allowed Grania and collaborators to perform the integrals that effectively decoupled, or at least iteratively solved, the system of singlet modes in Klebanov-Strassler. So this structure was noticed by Borokov-Gubser for that system. And what we're pointing out is just that this is true for any conformally Calabi-Yau background, even for the full second order PDEs, not just for singlet modes in Klebanov-Strassler. And this is not a consequence of supersymmetry or anything. Okay, so that's all very nice, but we can't really do anything with it if we can't even write the equations. So for a compact model, we can't even write down what the equations of motion are because we would need the metric. So to perform an actual calculation, what we need to do is use some sort of local approximation. So finally, we come to it. This is the scheme. This is our lamppost. We're going to take a conformally Calabi-Yau compactification with fluxes, which, after including a non-perturbative superpotential, is a non-conformally Calabi-Yau stabilized compactification. And we're going to consider a local region because here, at least, we can write down and solve the supergravity equations of motion. Of course, not every compact model will have a local region that looks like Klebanov-Strassler, but let's consider one that does. Then, using the tools that I just described, we can find a general solution in the throat region. So then any object that's localized in the throat region, some brain sitting there, will have its effective action controlled by this supergravity solution. Since we can compute the most general supergravity solution, we can find the most general form of the effective action. So now let's consider a model of inflation in which the inflaton is the position of a 3-brane. Actually, it has 6 positions, right? It has a radial position, it has 5 angular positions in T11. And we can find the most general form of the potential. It involves some powers of the radial position. The powers are the dimensions of operators in the dual CFT, times some known functions of the 5 angles, times Wilson coefficients. So here, the dimensions can be calculated building on foundational work by these authors. And these functions, these angular functions, can be determined. The problem is, even if you could compute what do these Wilson coefficients mean? Right. Well, this whole potential is representing the effect on D3 branes of moduli stabilization in the bulk. Right. The physics here is that Euclidean 3 branes here, or gaugino condensation here, interact with the 3 brane. They control the potential for the 3 brane. So if I were to move one of the Euclidean 3 branes around here a little bit, or otherwise distort the moduli of the bulk, or shift to some nearby vacuum in the bulk, that would change this potential significantly. It wouldn't change the deltas and h's, but it would change the Wilson coefficients. So we're faced with the following problem. Even if we could compute, which we can't, this list of Wilson coefficients in one particular compactification, what could we do with it? If you change then the bulk data just a little bit, the list of coefficients changes completely. So it looks like there's an absolute loss of predictivity. Okay, so that's where we seem to stand. But if you think about this for a minute, you recognize there are actually a lot of terms here for only 6 fields. And when you combine a lot of terms, hundreds of terms we'll find, depending on only 6 fields, the central limit theorem starts to take hold. So if we were interested in making only statistical predictions, we could do that even if we don't know the statistical properties of these Wilson coefficients. Okay, so this is not a standard approach to making predictions in a model of inflation in string theory, so I'm going to repeat. Since we don't know how to compute these in any given model, and even if we could, the particular form depends on the details of the bulk, how can we do anything? Well, we can construct an ensemble of potentials and ask whether it has any characteristic phenomenological properties. Then the thing which I would have to prove to you if I do that is that the characteristic properties that I deduce don't depend on the input statistics of the Wilson coefficients, which by hypothesis I don't have access to. And this is checkable, and it actually works. What we did is take this form and generate an ensemble of 70 million realizations of the system, keeping the first 333 terms. It turns out that the number of terms grows rapidly as you increase the dimensions, and at some point our numerical abilities failed, and so we stopped around here. Note that this is well above 6, right? So these include all of the important ones and start to include some terms that are not very important. And here is where the central limit theorem plays a role. If you're adding that many different terms, you can certainly expect it doesn't much matter whether you're drawing each coefficient from a Gaussian distribution or a flat distribution or what have you. But we verified that directly by just redoing this for different distributions and showing the results are the same. So what kind of behavior do we find? Well, we find, for example, a correlation between the tensor to scalar ratio depicted here and the spectral index. And so this is for some subset of these realizations. And for all of the ones that can be consistent with current observations, we do see a trend like this. We also see power law behavior. The probability of n e-folds of inflation goes like 1 over n cubed. So that allows you to ask the question, well, in this class of models, how likely is it that I see 70 e-folds if I know that if I condition on seeing 60 e-folds? Okay, so this is the kind of thing one can do. This is far from the last word on this class of models, but let me just summarize where these models stand, including some things that I didn't explain to you now, but I'd like to mention because they're actually very important for the motivation. The thing that I did tell you about is that local geometry makes computations possible. And the signatures of this model include cosmic superstrings, as explained by these authors and many others. Another really significant thing, remember the 3 kinds of deviations from the simplest model that I mentioned, deviations from Gaussianity, from adiabaticity, and detection of tensor modes. In this talk, I'm not going to talk about deviations from adiabaticity. Deviations from Gaussianity are really important, and in this context, I should mention, as famously shown by Silverstein-Tong and Alishaya, Silverstein and Tong, if the dBi kinetic term is important, then one finds a striking equilateral, particular shape of non-Gaussianity. The 3-point function has a particular form in momentum space. And this is one of the cases where string theory has suggested both a new mechanism for inflation, well, this is related to the earlier models of K inflation, and a new way of understanding how that can be robust and predictive. So this is an example to keep in mind. Now, this model that I described was not protected by any symmetry. I hope that was clear. I didn't explain this here, but when I drew 70 million realizations of the system, I didn't fine-tune anything. I just hoped that the computer would, by chance, find a model in which inflation occurred. And we find that happens. You get 60 e-folds about 1 time in 1,000, which is, in my view, not that bad. It's certainly not a natural consequence of the system. You don't just get inflation from writing down the Lagrangian. And that's important. We're going to see something different in a few minutes. And the phenomenology is statistically insensitive to UV physics, right? It didn't matter what the Wilson coefficients were. Now, if you think back to my motivation, you realize this has been a bit of a Faustian bargain, because how am I now going to learn anything about string theory from this model? It's statistically insensitive to the stuff that I wanted to probe. Right. Now, it's not true that all models of inflation are like that. But in this particular model, what we have is a well-motivated way of getting inflation in string theory that won't teach us much about string theory. So let's move on to a qualitatively different kind of model. This is a model in which the inflaton is an axion. Let me contrast this with the talk by Wilczek. This will not be the QCD axion. So if you like, you can think of this as just a pseudo-scalar. It would be the axion for some hidden gauge group. There are many other works on axion inflation. These are the ones that touch most closely on the presentation I'm going to give here. So large field inflation is interesting and important, as I stressed at the start, because it's very sensitive to ultraviolet physics. Remember, we have this divergent series in Taylor expansion in phi over m Planck. So the approach, really one of the few approaches that's controllable here is not to try and enumerate all of those terms. This is clearly impossible. But to identify a robust symmetry, one that's actually respected by the Planck scale physics, that protects the inflaton over a super Planckian range, right? And if you provide such a symmetry mechanism and establish that it's robust in string theory, then you really understand something about how large field inflation can occur. Let me explain the terminology. Large field inflation is a model in which delta phi is bigger than m Planck. These are precisely the models in which primordial tensors can be seen. And let me stress, even if you thought these models are not very appealing, you think that they sound too complicated, recall that the next generation of observations, the coming generation, could force us to think about them in fortunate circumstances. Okay, so the old idea, due to Friis, Freeman, and Olinto, is that a Peccei-Quinn symmetry could protect the inflaton potential over a super Planckian distance. And what we're going to do is ask, can we UV complete this? Or is it inconsistent with what we know about UV physics? So, as you know, it's very easy to find axions in string theory. You just integrate a p form over a p cycle. And they typically enjoy an all orders shift symmetry. And remember, this doesn't depend on supersymmetry. This shift symmetry argument depends on the absence of boundaries, i.e. There shouldn't be any D-branes in the system to which the putative axion could couple. And it's an all orders in perturbation theory, but it doesn't hold non-perturbatively. So both of those things are going to matter for us. We're going to find models in which we violate both preconditions for the shift symmetry. Namely, we will consider non-perturbative contributions, and we will consider the inclusion of boundaries for the world sheet. And playing those things off against each other is what's going to allow us to control the models. So the non-perturbative effects, just as in QCD, will break the continuous shift symmetry, generating a periodic potential. So A is the dimensionless axion, phi is the dimensionful axion, dimensions of mass, and F is its periodicity, right? And you can compute the periodicity from compactification data. Again, since this is not the QCD axion, the astrophysical constraints that you heard about in the very nice talk by Wilczek are not applicable. The scale in front here is not the QCD scale, right? It's a much higher scale. So those constraints don't apply. So where do we stand? Well, if you just write down a model like this and say, could this drive inflation? You very quickly find that the slow roll parameters can be small. They can be small if the axion decay constant is large in Planck mass units. Is that achievable? Well, no, not presently. And it's actually not hard to see why that is. Remember, the axion kinetic term here comes from, well, the decay constant is really the normalization of the axion kinetic term. And we know where the axion kinetic terms come from. For example, for B2, we have an H3 wedge star H3 kinetic term. And so you just take that term, you dimensionally reduce it, and you see what does F turn out to be in Planck mass units. And the way it turns out, as these authors noticed, is the following. The decay constant in Planck mass units always goes like a non-negative power of the string coupling divided by a non-negative power of a volume. And the trouble there is that weak coupling in large volume, this is going to be small in Planck units. So you certainly can't achieve F much bigger than m Planck. In fact, it's not that easy to obtain F that's actually very small. But very small here means very small compared to the gut scale. And what will be relevant for us is models where F is between perhaps 10 to the minus 2, 10 to the minus 1 times the Planck scale. Okay, and these are arguably under control. So this is not possible in presently computable limits of string theory. Maybe we'll have a better idea someday. But right now, there are two ways of thinking about getting around this problem. Okay? And both of these ideas are, I think, worth considering, and they're also worth further technical development. So the individual decay constants are too small, meaning that we have some Axion potential, which is a cosine, and moving over one period of the cosine doesn't drive inflation. You've got two choices. You can have a lot of axions and have a collective excitation of the axions drive inflation. Or you could take a periodic potential like this and tilt it. Move over several axion periods. Move multiple times around one axion circle. So those two ideas, the collective excitation is building on assisted inflation. This is called N-inflation, proposed by these authors here. And the other idea is to traverse many periods of a single axion. So that's Axion monodromy. And you can compare that to the first monodromy model proposed by Silverstein and Westphal, which is a model of D-brane monodromy. I won't be talking about this model in detail. All right, so what I'm going to tell you about is Axion monodromy. How can you make that work? Well, consider a compactification, let's say a Calabi-Orientifold with a fivebrane wrapping a curve, and define little b to be the integral of b2 over that curve. So you write down the Born-Infeld action. The Born-Infeld action looks like this. And you see the Born-Infeld action is just not invariant under shifts of b. Right? Any would-be shift symmetry of b is completely gone. And if you take b to be large here, then the dominant term inside the square root is little b squared. Take the square root. It goes linearly. So the potential is a little more complicated near the origin, but asymptotically it's linear, and it looks like some mu cubed phi, where mu is a mass scale that you can compute in terms of the tension of this wrapped fivebrane. Okay, so the key point is that the fivebrane contribution is not periodic. As the axion goes around one period, the potential undergoes a monodromy, and so the field space, instead of being a circle, is a spiral staircase. Right? And the slope of the spiral staircase is linear. That's where this potential is coming from. What we find is that in relatively controllable models, if you make 100 circuits around this staircase, you can find a displacement of order 11 m Planck. I pick 11 because 11 is what you need in a linear model of chaotic inflation to produce 60 e-folds. So if I wanted a model with more, I would need more e-folds. I would need to make this initial VEV a little bit bigger. Okay, and clearly what's happening here is some sort of symmetry is protecting the flatness of the potential. And we're going to have to investigate that in more detail. Okay, so how can we construct a compact model? You may be saying, wait a minute, how are you putting a fivebrane on a curve in a compact model? Isn't there a tadpole? Yes, I'd need to wrap a fivebrane on one curve and an anti-fivebrane on a fivebrane with opposite orientation on a homologous curve. And so we'll use the metastability proposal of these authors, in which there's a larger representative in between these two curves. And so the branes have to tunnel in order to annihilate. So that in itself looks fine. Now we need to attach this to a KKLT compactification. So find a region of a KKLT compactification that has a family of curves like this. And then we need to compute the moduli potential. So this is now the subtle point. We have to really work out the potential in some detail. Okay, remember I said at the start you have to get everything up to at least dimension 6, so let's do that. Building on what's known about dimensional reduction of these sorts of orientifolds, we quickly find that the moduli potential gives a fatal delta equals 6 contribution to the potential for this putative inflaton B. Okay. The inflaton masses of order of the Hubble scale, inflation fails completely. However, if I take the configuration which is C2 instead of B2, so little c is the integral of C2 over the curve, this is the Ramon to 2 form, then C doesn't actually appear in the moduli potential at leading order. And that is the shift symmetry in action. That's what had to happen, right? It's all very nice to say that in an unstabilized compactification, there's a so-called symmetry that protects some field. What one has to show is that upon stabilization, upon coupling to dynamical 4D gravity and fixing all the moduli potential also respects that symmetry. And that's what we're finding here. There was a would-be symmetry for B and C, and we find that upon compactification, only the symmetry for C survives. So what we actually have to do is take an NS fivebrane pair rather than a D fivebrane pair, and take C to be the inflaton. So the story now is the following. I have now an NS fivebrane wrapping a curve, actually a tadpole canceling combination of such. And the initial configuration I start with is just a large VEV for the RR 2 form C. So I wind up the system like that. The branes are just sitting in place. They stay in place the whole time. I wind up the system, it absorbs energy, I release it, and it slowly spirals down, inflating. Of course, what one has to check is that there aren't steeper directions. And so that's what we checked. Okay, so the leading C dependence in the effective action comes just from the fivebrane tension, and so the leading part of the potential is linear, but that's not all. There are more terms in the potential. The potential also has sinusoidal contributions from the non-perturbative effects that we were talking about before. Remember, there are two ways the shift symmetry can fail. There can be a boundary, well, we added a brane, or there can be a non-perturbative effect. So it's not at all hard to find a regime of parameters where the non-perturbative effects, quite naturally, are small compared to this hard slope. What you get then is a picture of a slope with small modulations. And then these modulations do something interesting. They produce a driving force that resonates with the oscillations of modes inside the horizon. So I didn't explain what the oscillations of modes are. You know that in inflation, the perturbations are oscillatory inside the horizon, and eventually, as they stretch toward the horizon, they freeze and stay frozen. So while they're inside the horizon and oscillating, they can resonate with the frequency of going over these bumps. 10, okay. When that resonance occurs, what one finds is a resonant production of the resonant perturbations of the spectrum and bispectrum. So it looks sort of like this. So I'll just sketch the picture briefly. Instead of just the acoustic oscillations, one gets a spectrum of ripples on top of that. All right, so that's nice. And so here, one can develop a prediction here with reasonable theoretical error bars, which is, of course, the whole point. And it's consistent with observations so far, and we could easily rule it out in the near future. Okay, I don't have much time to talk about eternal inflation except to say that it's an extremely important subject where it's not yet clear that the essential issues have been resolved, and people are working hard on it. Okay, so now let's talk briefly about the initial singularity and alternative cosmologies. So the two broad approaches we could take, we could either try to embed inflation in a string compactification, as I've described now at length, or we could try to develop a computable understanding of the Big Bang singularity. So let's try the latter. If we do that, we really have two kinds of choices. We can try and study toy models of the initial singularity whose cosmology is totally unrealistic, couldn't possibly produce the observed perturbations, might not even be four-dimensional. But in models that are computable in string theory, really honestly computable, and this has been an active area. The other thing we could try and do is construct a model that looks phenomenologically plausible, but where string theory is not quite useful yet, but can be appealed to. And so I'll briefly talk about these models, and then I'll have a few comments about these sorts of approaches. So the first approach is to find a comparatively tractable singularity, so some null singularity in a Lorentzian orbifold or an exact plane wave or anti-de Sitter space, and then use either exactness in alpha prime or ADS-CFT or something like that to try and understand, really using string theory, can we resolve these singularities? Okay, and this seems like a great idea. The thing is, in many cases, there's a singular crunch upon adding even one particle or string. And more generally, even if that weren't the case, you don't see here anything that looks like our Big Bang. You see mostly null singularities. Well, you see exclusively null singularities here. So these tools are impressive, and I think this is a great direction where progress could be rather striking if someone has a really good idea. But much work is required to connect these to the observed universe. The other thing one could try is to consider slightly alternative cosmologies, ranging from inflation plus lambda CDM to models that stretch the boundaries of naturalness, or even trespass those boundaries, to more ambitiously even just reformulating QFT plus GR, or considering things that are even more speculative. And so what I'll be talking about very briefly is models that are not really revolutionary in any sense, but they push the bounds of what we think is reasonable in effective field theory. And in many cases, they violate expectations from field theory. So the idea here is to try and replace the Big Bang singularity with some sort of bounce, a transition from a prior contracting phase through a bounce that's somehow nice and controllable to an expanding phase. And the idea is the perturbations should come out of that bounce. So this has been an important subject. And the thing is, when the low-energy Einstein equations apply in a Friedmann-Robertson-Walker universe, you can show, since well, you'll easily see, you need A double dot to be positive and A dot to be 0. And you see, unless the curvature is positive, the bounce requires a violation of the null energy condition. And that's bad news. That generically leads to instabilities, either tachyons or ghosts. So you might have heard, there is a proposal for how to get around this, and let me briefly state what the status is. The proposal is to use a ghost condensate, as suggested by these authors, to support a non-singular bounce, as explained by these authors. The thing is, the UV completion of the ghost condensate, which after all is the sort of topic we're talking about today, how does this relate to string theory, is highly questionable. It appears, as explained by Arkani Hamed et al., to violate our ideas about de Sitter thermodynamics. And there's also no hint that this could be realized in string theory. But let's leave that aside. Suppose we allow a ghost condensate phase. Even then, Steinhardt and Schwey have recently shown that quantum fluctuations generate anisotropies that lead to an anisotropic crunch. The point here is that during a contracting phase, anisotropies grow. If the contraction lasts long enough, or the initial anisotropies were large enough, then one ends up with an anisotropic crunch rather than a smooth bounce. All right, so that means there's no evidence for a controllable bounce in a UV completable effective theory. But hope springs eternal. What if we say, wait a minute, this is all a consequence of the low energy Einstein equations. Let's just dispense with the low energy Einstein equations and bounce at high curvature. So that sounds bad because we've just reviewed the status of singularity resolution, cosmological singularity resolution in string theory, and we didn't see any nice bounces from a contracting phase to an expanding phase through a would-be space-like singularity. Nevertheless, one does see claims that string theory produces bouncing alternatives to inflation, and these models are string-inspired. So they invoke potentials for ekpyrotic phases, dark energy phases, even ghost condensate phases, and say that they're motivated by string theory, but in fact, the calculations that obtain these in string theory have not been presented yet. And moduli stabilization is typically ignored. All right, so this is not so good, but here, at the critical juncture, the really important point, when the bounce that's singular in supergravity, which is after all the problem we were trying to deal with, when that bounce arises, string theory is appealed to. But again, we don't actually have a calculation in this context. So I think it's important to describe this point because the space of models of inflation and alternatives to inflation that are broadly speaking inspired by string theory is vast. And there's a big distinction between the models that really are, in some sense, computed in string theory. We can compute almost everything in string theory. And the models where really all that's taken from string theory is the hope that there could be some resolution. So it would be very nice to have an alternative to inflation. But right now, the constructions that have been presented have not been subjected to the same sorts of tests. I don't mean experimental tests, but the same sorts of theoretical requirements the models of inflation have been subjected to. So the status then is there's no evidence that the proposed background arises in a string construction, just the homogeneous background. Instead, one tends to find either crunches or singularities that are not understood. And then, most importantly, one often hears that these models will be falsified with some new data. And that is a claim that's difficult to believe because the perturbations were created before the singular bounce, and they're propagated through a singularity that's not yet been understood. So it's hard to believe that one could really understand how that works without actually calculating what happens at the singularity. Okay, so I don't have time to talk about string gas cosmology, so let me conclude. Why should we think about string cosmology? Well, as I explained at the start, QFT plus GR models of the early universe are sensitive to Planck scale physics. And string theory might illuminate or resolve the initial singularity. Another point which is very promising, but which I didn't say much about, is that tools like ADS-CFT could help us to understand inflation and conceptual problems in eternal inflation, conceptual problems about quantum gravity in de Sitter space. String theory can also inspire novel cosmological scenarios. That is to say, these are scenarios that could have been written down in the past in field theory, but in practice were not. New mechanisms can be suggested, and some of those mechanisms are Planck-sensitive. So even if they had been written down years ago in field theory, it would have been hard to understand whether they were robust. Building them in string theory, we can see that some of these mechanisms are indeed robust. At the same time, these models have led to possible novel signatures. And these connections might turn observational cosmology into some sort of admittedly narrow window on string theory. So that's the why. What's the how? How do we do string cosmology? Well, the basic requirement that I've been trying to stress throughout is one needs a clear understanding of the dynamics of moduli. That's not all. Once you stabilize the moduli and find a stabilized vacuum, you need to compute the effective action, including Planck-suppressed contributions. For small field models, you can stop after a finite number of terms, but those need to be obtained. And for large field models, one really needs some sort of symmetry argument, or a similar argument avoiding an infinite series of contributions. So the alternatives to inflation are often inspired by string theory, but they've not yet been realized in string theory. And making these models, or alternatives to these alternatives, quantitative and predictive, is an interesting open challenge. It would be very nice if someone could develop a non-singular bouncing model in string theory where we can compute everything. Much work remains before we can understand what sort of cosmological dynamics is generic in string theory. So I don't think the conclusions one would reach about string cosmology would be all that different at the time of strings 2012. But I think by strings 2013, they will be completely transformed, because by then we should have a full sky map of the CMB from Planck. So stay tuned. Thank you.
Yeah, thank you very much for this nice overview. We have time now for questions.
You studiously avoided it in your talk, but could you say a few words about the state of isocurvature fluctuations?
The difficulty with, okay, so let me actually remark about the connection of isocurvature perturbations to string theory and constraints in that scenario. It's possible to write constraints on isocurvature fluctuations coming from axions, as you well know, and WMAP does provide constraints on these. However, from my point of view, that's not perhaps the most interesting parameterization of constraints on isocurvature for the purposes of discussing inflation in string theory. That's because what string theory is certainly seeming to tell us is all of these models have a large number of light scalars. And when you make one of these scalars light enough to be the inflaton, in general, you don't manage to make all of the other scalars ultramassive. They tend to go together. The mechanism that makes one light makes a lot of them light. And so I think a very generic expectation should be some kind of isocurvature. However, here I want to distinguish visible from invisible isocurvature. These are what string theory models with multiple light scalar fields, in fact field theory models with multiple light scalars, certainly suggest is you should have entropy perturbations in the primordial phase. But if all of that stuff decays through some portal in some way, then you're not going to see it in terms of differences in dark matter and photon densities now. It's all invisible isocurvature. WMAP can say nothing about it from their examination of the two-point function. What you can see, though, is that contributions like that, entropy perturbations like that, can evolve, well, can source outside the horizon evolution of curvature. And that can be tracked in the non-Gaussianity. So I think the interesting way of getting at effectively isocurvature, although invisible isocurvature perturbations, is by looking at the three-point function and seeing evidence. For example, if you see the so-called local non-Gaussianity shape, then you would have firm evidence that there were multiple light scalars. I think that's the most interesting kind of isocurvature for these kinds of models.
Other questions or comments? No more questions? So then let us thank you again.